Fossil fuels, such as coals, oils, and natural gas, are the major energy source used today. The problem is that humans have burned too much fossil fuel for the last hundreds of years, and now humans are posed with a dire threat: global warming. Global warming is literal warming of the planet due to the responsibility of the humans living in it. However, this bleak situation could be avoided if and only if we use nuclear energy instead of burning fossil fuels. Because burning fossil fuel is very harmful towards the environment and is a major contributor in global warming, nuclear energy on the other hand is the more environmental friendly and more beneficial in many aspects. Although there are many downsides in nuclear energy, like the very long time spent in construction and plants and the expensive prices, in the long run it is outstandingly worth it. Fun fact: 1 kilogram of naturally occurring uranium has the energy of almost 19,000 kilograms of hard coal, or 12,000 liters, or 63 barrels of oil, and enables the generation of like 45,000 kilowatt per hour of electricity. So, how are nuclear energy made? It is brought about by the reaction of elements when they do nuclear fusion and fission. Now, what is nuclear fission and fission? Nuclear fusion is a nuclear reaction in which two or more atomic nuclei are subjected to high heat or pressure, and because of their excitement, they heat each other at high speed at a very high energy and fuse together into a new nucleus. And when they hit each other, Coulomb's force, the force that keeps protons apart, is conquered. The fusion of hydrogen in lower temperature stars like our Sun involve the following reactions yielding positrons, neutrinos, and gamma rays. Normally, fusion is not possible because the strong and repulsive electrostatic forces between the positively charged nuclei prevent them from getting close enough together to collide and for fusion to occur. The mechanism, how to overcome the Coulomb barrier, is by the temperature and by the pressure. At close distances, the attractive nuclear force allows the nuclei to fuse together. Nuclear fission. Nuclear fission is the splitting of large atoms that are very unstable and can be split up by firing a neutron at them. To start the process, one of the most important fission reactions is uranium-235. The fission of uranium-235 starts off when flying neutrons hit the nucleus, forming a highly unstable compound resulting in uranium-236, which immediately splits into two lighter elements such as krypton-91 and barium-142. Through this process, it also releases 3 or more neutrons in energy. Now, these remaining neutrons being released as high-energy particles can then go on to continue the process of fission, attacking another uranium-235 atom and maintaining a chain reaction. An atomic bomb's core is composed of 2 parts, radioactive isotope and TNT, or what you call as trinitrotoluene. These isotopes could be either uranium-235 or plutonium-239. Because these elements have unstable isotopes, that would imply that these atoms have more neutrons that would hasten the chain reaction. The covering of the isotope, which is a TNT or trinitrotoluene, is the explosive compound that would trigger the escape of the neutron from its atom, and then splits nearby atoms. It would start the chain reaction that takes 18 picoseconds, which is 1.8 times 10 to the power of negative 11 to occur, and this gives off an amazing amount of energy. The bomb has given a massive impact that creates a huge crater full of harmful radiation, such as electromagnetic radiation and ionizing radiation, which can cause cancerous tumor brought about the penetration of human cells. Thus, a fallout is manifested, meaning a peak of toxic radiation brought about that the explosion fell back from the sides of the room. So, how do nuclear power plants work? A worker loads uranium fuel into a reactor core. Starting the chain reaction, neutrons attack it, which can continue as long as fissionable fuel remains in the core. The neutrons in the chain reaction explore at many different speeds, yet the moderate ones work best in splitting uranium atoms. The core sits in a moderator that slows the neutrons down. Reactions to be kept cold and steady so that the reactor generates heat without getting excessively hot. Controlled rod will be then moved in and out of the reactor core. The rods are made of materials such as cadmium and boron that absorb neutron and slower stop fission as needed. Reaction of it would become excessively hot, so a coolant circulates through the reactor core to cool it down. The coolant gets hot, yet this is exceptionally a very useful heat. The coolant boils into high-pressured steam. The pressure pushes the steam to its turbines, then the energy of the spinning turbines becomes electricity.